We go with for the last presentation, Fui Shen, okay, Anisotropic plasticity, an experimental and numerical investigation of the anisotropic plasticity and fracture properties of high-strength steels from laboratory to component scales.
Thanks, Mr. Chairman. My name is Fu Huishen, and together with some colleagues from RWTH Aachen University, we have performed an experimental and numerical investigation on the anisotropic plasticity and fracture behavior of high-strength steels, and today I will present you some results. So in the beginning, I will give a short introduction about our study and followed by an overview of the material and experimental program. After that, I briefly explain our material models, and then we can have a look at some results. So what is anisotropy? Briefly speaking, it describes the phenomena that when the material is loaded along different directions, it will behave quite differently. So that is anisotropy. And one good example to visualize the anisotropy effect is the cup drawing process. For example, due to the existence of anisotropy, there may exist some earring. And this is not desirable for industry because it's not only a waste of material, they have to cut this out part, and it also has some risk of failure in those points. And for the another aspect that if we load the same geometry along different directions, we can find that the same material along different directions, the force is different, and the fracture displacement is also different. So this means that the fracture is also affected by anisotropy. And therefore, we need to give a better description of anisotropy. And from a previous investigation, we have found that due to the evolution of macrostructure during forming process, the anisotropy is also evolving. And so we ask ourselves whether this evolution of anisotropy is critical for their mechanical properties, and if so, how can we characterize the plasticity and fracture behavior while keeping the anisotropy evolution in mind? And the material we use is X70 pipe materials, and the chemical composition is shown in this table, which has low carbon content and several alloying elements. The material was initially supplied in a heavy plate, which has initial thickness of 14 millimeter, and after that, a 2 millimeter thin sheet was manufactured in the middle part of the plate, and all the specimens that are used later on are manufactured in this sheet along different directions. And the macrostructure of this alloy is ferritic magnetic structure, which is quite typical, and it has some carbons inside. And then we perform some uniaxial tension test along different directions. For example, in this figure is 3 direction along rolling direction, transverse direction, and diagonal direction. These are the other 4 directions in between. And we can find that the flow curve is always the highest along the transverse direction. And during uniaxial tension test, we also measure the R value, also called Langford coefficient, which is the ratio between width strain over the thickness strain. And we find that the R value is the highest along the diagonal direction. And then if we plot the normalized stress over the loading angle, we find that the anisotropy is actually evolving. For example, the black one shows the distribution of yield strength at the beginning of plastic deformation. The minimum point is at 30 degrees, while with further plastic deformation, it shifts towards 45 degrees. So we have to take the anisotropy evolution into account. And this is the experimental program that we use on the lab scale. As we all know that the damage and fracture behavior are affected by stress state, therefore we have applied various types of geometry to cover a wide range of stress state, and we perform the test at room temperature called the static loading rate along 3 different directions. And this is an overview of the specimen that I have used. We have a smooth stock bone to calibrate the flow curves, and 1 central hole specimen, 3 notch stock bone specimen with different notch radius here, and 2 plane strain specimens. And on the component level, we also apply the drop weight tear test, which is a typical method in the pipeline industry. And in this experiment, a big heavy hammer falls down with a velocity higher than 6 meters per second, and it impacts the specimen at different temperatures. So after the experiment, the fracture surface on the specimen are analyzed, and these experiments are conducted along different directions. And then let's have a look at those results. These are two different geometry specimens. One is central hole specimen, the other one is notch dog bone specimen with radius of 10 millimeter. And as we can see in both specimens, the force is always highest along this transverse direction, which is due to the higher flow curve. And the fracture displacement is always the largest along the diagonal direction. And so this is the experimental observation of anisotropy. And on the component scale, we have analyzed the shear fraction on the drop weight tear specimen, and we performed the test at different temperatures, and clearly it shows a transition behavior from brittle to a ductile fracture. And also this transition behavior depends on the loading direction. For example, in this case, it seems like the 45 degree shows more brittle behavior here. So in conclusion, we have found this anisotropic damage and fracture behavior in this material. And then we come to the material model we want to apply. As we know that for an accurate description of damage and fracture behavior, we have to apply, first of all, an accurate description of their plasticity. Therefore, in this study, we have used an extended version of the conventional Hill 48 model. So starting from the isotropic Mises model, Hill has introduced 6 anisotropic parameters to characterize the anisotropy effects. And he has given different ways to calibrate these parameters. One way is to use the uniaxial tension test during from different directions to calibrate these parameters, and the other way is to use the R value from uniaxial tension test along different directions. But there is a shortage of this model, because if you use yield strength to calibrate those parameters, it cannot describe the R value distribution properly. So in order to overcome this shortage, some researchers have proposed the non-associated Hill 48 model, in which they apply, for example, the stresses to calibrate parameters in the yield function and R values to calibrate those parameters in the flow potential in such a way that the yield function and flow potential is getting separated. And there we can see that the yield locus and flow potential is different in this model. And yield locus is used to, for the stress update, while flow potential determines the flow direction. And last year, based on the non-associated Hill 48 model, we have made a further extension by making those anisotropic parameters dependent on the plastic strain to take into account of anisotropy evolution. Therefore, for example, this is a figure we get from last material, and with the further increase of plastic deformation, we can find that the difference between the yield locus and flow potential is getting more obvious. So I would say this model is more promising. And for the damage mechanics model, we used a hybrid damage mechanics model, a modified version of Bivesbicki model, as explained by my colleague earlier. And we have a scalar damage variable D to calibrate the damage-induced softening and fracture behavior. And in this model, we can include temperature effects and strain rate effects also. And in order to take the anisotropy effect into account, we applied the anisotropic equivalent stress. And also, we used the non-associated flow rule so that both R value and flow stress can be accurately described. And instead of using detailed equations, I would like to explain or model with the help of this figure. So it can also describe cleavage fracture, but I do not want to focus on that part. And for any ductile material, after a certain amount of plastic deformation, we assume that ductile damage initiation may occur. And it occurs once there is a somehow criterion called damage initiation locus, which depend on stress tractility and load angle parameter. So with further plastic deformation, once this locus is reached, we assume damage initiation occurs. And after that, damage softening takes place, and the damage softening evolution or rate is controlled by energy dissipation theory. So with further deformation, once another criterion called ductile fracture locus is reached, then the final ductile failure is triggered. So this is a quite simple approach, and it can be switched back to coupled or uncoupled approach by manipulating these parameters. Okay, so before we go to investigate the damage and fracture properties, let's check the accuracy of this plasticity model. The first step is to check whether it can describe the distribution of stress and R value properly. So this is the prediction at strain of 0.02, and another one is at strain of 0.06. So it can describe the anisotropy pattern at different strain levels, and it can also describe the evolution of yield locus and flow potential quite properly. Then we want to compare the simulation results between different plasticity models to check their validity. So we start with the isotropic misses one, and then some results for the anisotropic conventional Hill model. And finally, we also run a simulation with our new model, Hill 48 model. And then we make a quantitative estimation about the error in the false prediction at the maximum force point and several points after the maximum force. And we can find that the error predicted by the Hill 48 model is the smallest. So this gives us information that this Hill 48 model can be capable of describing the anisotropy plasticity behavior of this material. And then I would like to use one specimen called notch dog bone with 10 millimeter radius to show you how can we calibrate those damage fracture parameters. So we first run a simulation using only plasticity model, and then we can identify the damage initiation point, extract all those PEQ and stress state parameters from critical element at this damage initiation locus moment. And then after collecting all those variables from different geometries and different angles, we can find damage initiation strain depends not only on stress tractility and load angle parameter, but also affected by loading directions. And with the help of this equation and all those values we have so far, we can construct 3 damage initiation locus for different angles. We can find that the DIR for the rolling direction is the highest comparison with other angles. And next step is to determine the damage evolution rate, which is controlled by GF factor. And by adjusting this factor, we can properly describe the damage-induced softening in this region. And then in our experiments, we can identify, so this is the final point for the ductile fracture. And then by applying a similar approach as we define the DIR, we can extract all those damage variables and local stress state parameters at the ductile fracture moment, and use those variables, we can construct the ductile fracture locus for 3 different angles, and then we can run a simulation with all of those damage and fracture parameters inside. As you can see, for example, in this 90-degree, the final crack propagation is exactly predicted in our model. And here is a comparison between 3 different orientations, so we can achieve quite a great agreement between experiments and numerical results. So this is the same geometry, and we can see our simulation can predict the crack propagation properly. And these are results for to other geometries. You can see crack initiates here and propagates along this horizontal line. And this is the simulation for the plane strain specimen. So in general, I would like to conclude here that we have observed anisotropic damage and fracture in this material, and we used an evolving plasticity model to describe this anisotropic plasticity behavior of this model, and it works quite well. And then we further extended it to anisotropic damage mechanics model to describe the final fracture behavior of this material. So it works quite well. Yeah. So thank you for your attention.
Thank you. So now we can start with the discussion.